All right, good morning, folks. Welcome back to Introduction to Algebra. This is Mike Filipski coming at you with another video. In the previous video, we talked about solving quadratic equations, specifically using the zero product property. In this video, we're going to start a new section in a new chapter, and we're going to talk about the fundamental property of rational expressions. But first of all, I think we need to clarify some terminology here. What the heck do we mean when we talk about a rational expression? A rational expression is an expression of the form p over q, where p and q are polynomials, and q, the bottom, is not just 0. So here are several samples of rational expressions. X plus 1 over x minus 5. The top and the bottom, p and q, are polynomials, and the bottom is not 0. 5 over x plus 2. You can certainly have just a number in one part, either the top or the bottom, as you see here, and then a polynomial on the other part. X squared plus x plus 1 divided by x squared minus 3x plus 2. We have a polynomial on the top and bottom. The bottom is not 0, so we're good. And 2x cubed over 5. So basically what we see happening with these things is basically they're just fractions, except now in at least one of the bottom or the top, we have our variable being brought in some way. So basically, a rational expression is, at its core, a fraction, but now we have variables being brought in. We have polynomials, like these quadratics here, or x plus or minus some constant. Now, there's a big difference between polynomials and polynomial expressions, the things that we talked about in Chapter 4 and Chapter 5, and rational expressions. Rational expressions have the possibility of being what's called undefined. And what we mean by undefined is that this thing that we have here, this rational expression, if you try to plug in a particular number, you may not be able to get any value back out. For all of the types of things that we've worked with up until this point, you could take any number whatsoever and plug it in, and you just do some small calculations, and you would get some number or some value back out. Well, this is the first case where, based on the number you plug in, you may not be able to get some number or some value back out. And we would say that at that particular value for our variable, the rational expression would be undefined. And what really tells us when the rational expression is undefined or not is if the bottom, if the denominator is equal to 0. Because we know that we cannot take something, we cannot take any number whatsoever on top, like say 7, and divide it by 0. That's not good. Can't have that. Don't know how to work with that. So it's important for us to find out what values for our variable, like, for example, typically our variable is x. It's important for us to know what values make a given rational expression undefined. We need to find what those values are, and we cannot plug in that number or those numbers or those values into that particular rational expression. So to find what x value or values make a rational expression undefined, you're just going to set the denominator, or the bottom of your rational expression. You're going to set it equal to 0, and you're going to solve for your variable. So here is one example. We're going to find the x value or x values for which x squared plus 1 divided by x squared minus 1 is undefined. So what I'm going to do is I'm just going to take the entire bottom and I'm going to set that equal to 0, and I'm going to solve for x. So x squared minus 1 is equal to 0. If you think back to some of our factoring techniques from chapter 5, this is a difference of two perfect squares. X squared is obviously x squared, and 1 is 1 squared. So by the difference of two perfect squares, this factors into x plus 1 and x minus 1. So each of these factors we found, the product is equal to 0, which means either factor on its own could be 0. So I set each factor equal to 0. X plus 1 equals 0. And x minus 1 equals 0. And then we find that x is equal to negative 1 and x is equal to positive 1. So these are the two values for which this rational expression right here is undefined. We cannot plug these two values in and get something back. So we can just note that they're undefined at x equals negative 1 and x equals positive 1. We'll do a couple more here. Again, same thing. All we have to do, we'll start with this one here. All we have to do is we just have to take a look at the bottom of our rational expression and just set the bottom equal to 0 and then solve for our variable x here. So again, I'm just going to take the bottom, set it equal to 0, and I'm going to solve for x. And this is going all the way back to chapter 2, so we should be very comfortable with this by now. It's pretty straightforward and pretty easy to find that x is equal to negative 7/3. So this is the one x value that we cannot plug into this rational expression right here. Right there. And this one here, again, you're just looking at the bottom. You're setting it equal to 0, and you're solving for x. Well, x squared equals 0. We're asking ourselves what number times itself will give me 0. Well, the only way that can happen is if you have 0 times 0. The only way you can get 0 by multiplying is to have at least one of our numbers be 0, and these numbers have to be the same thing. So 0 squared gives me 0, so x equals 0. So that's what we have for that one. Sometimes you don't have to worry about any values where the rational expression is undefined. Sometimes the bottom of your rational expression, sometimes there are no x values that will make the bottom equal to 0. And that is one case of what is happening right here. X squared plus 4. We cannot break that down into any two factors. There are no x values that will make this thing equal to 0. So this guy is defined everywhere. That is to say, we can take any x value whatsoever and plug it into this thing, and we will get something out. But I'll let you try this one here on your own. So I just want to do a little bit of a recap of a term here. A rational expression is in lowest terms if the greatest common factor between the numerator and the denominator is 1. That is to say you have fully canceled out any common factors between the bottom and the top. And now the big property for this section, that is the title of this section. So how do we get rational expressions in this lowest terms? How do we get them as nice as possible? And we do it with the fundamental property of rational expressions. Now, this thing has a fancy schmancy name. We have been using this property all throughout this course, and you've even been using it prior to this course. So the property itself is not new, perhaps just seeing the name is. If P over Q is a rational expression and K is any polynomial that's not 0, then P times K over Q times K is equal to P times Q. Now, that's a very technical, mathematical way to say the following thing. Basically, all that property is saying is that we can divide out common factors in the top and bottom of the rational expression, including factors that contain variables. Now, we've been doing this just with numbers up until this point, but the same thing works with these rational expressions and these variables here. We've done things where we have, say, 12 over 20, and we have to simplify that fraction, and we think, okay, what are sort of the common factors between the top and the bottom? So perhaps we'd start off and say, oh, okay, so 12 is 2 times 6, 20 is 2 times 10. Okay, there's that common factor of 2. We can cancel that out, and that gives me 6 over 10. Okay, we can simplify this further because 6 is 2 times 3, 10 is 2 times 5. Again, there's a common factor of 2. Can cancel that out, and now we have 3 over 5, or 3/5. And that is fully simplified. We are doing this exact same thing. We're still canceling out common factors on the top and the bottom, but now we're going to see that we can do this with factors that contain variables like x, or x plus 2, or x minus 3, or something like that. Those types of things now we can also simply cancel out. But we're going to pause here for now. We'll pick up with seeing samples of this in our next video. If you have questions or comments, please be sure to reach out to me, guys. Emails, voicemails on my office phone. Stop into my office hours, stop into my tutoring hours. Flare signals, SOS bonfires, signs flying on the backs of planes, whatever you have to do. Until the next video, take it easy, guys.